We have a strike angle of 35. A dip angle of 60. And then we have the coordinates for the top and bottom edges of the rupture plane. So we could just copy and paste them here. Just be careful that you're actually inputting the top left and top right and bottom left and bottom right coordinates in the correct cells. If you have more than one plane describing a rupture, you can add more surfaces and again put in the coordinates for those extra surfaces. But here we have a single planar surface, so we have all the information that we'd like to provide here. So in that case, you should just click on the convert to Nrml button at the bottom. The Nrml is the OpenQuake format, which is a variant of XML. So if you click on convert to Nrml, you should see a display showing you what the input file looks like. And you can download the file using the download button. So by default, it goes into your downloads directory with whatever you set it up as the default download directory on Windows or Mac. So on my machine, it goes into the downloads directory, but it could be a good idea to save these into the scenarios folder in the workshop exercises directory so that you keep track of where the different files are. Otherwise, once you start working with multiple examples, your downloads directory can get cluttered. So I'm going to move this rupture file into my scenarios directory for the shallow magnitude 7.0 scenario. So I will cut and paste it here. If you wish, you can rename the file to something that you can recognize easier in the future. So here I'll just rename it to rupture underscore shallow. So just move the file into my scenarios folder and renamed it to rupture underscore shallow, just so that I can find it easier once we start having many of these files. Okay, so if you like, you can just see what this file looks like. If you're interested, you can open it in a regular text editor. So this is what you'll see inside. This is just the information that you just provided about the rupture, but structured in a way with some metadata information that OpenQuake can recognize. So you don't need to use the input preparation toolkit. If you are, once you get comfortable with these input file formats, you can build these using your own tools or just by editing them in a text editor. Let me zoom in a bit. So you'll see the magnitude of the event, the rake angle, the location of the hypocenter, and then the coordinates of the planar surface that we input. So it's a very simple file structure with some metadata tags as well. Again, I'll pause here for a bit if anybody has questions. Okay. So we've got the basic rupture geometry that we need to run the scenario. So we're ready to start running some quick calculations. Catalina just informed me that on the website for the workshop, if you click on data sets, we've added a spreadsheet that has a few, let's say, motivating questions for today's exercises. So it has It has a few tables that you can start populating based on what we do in this session, and then for the other two scenarios as well. Some questions about what would be the maximum PGA that you see in the whole region for different GMPs, for different site conditions, for different intensity measure types, and using different assumptions. So this is something that you can use to, if you're already familiar with OpenQuake, then you can start trying to fill up these tables for the three scenarios. So we'll do the same thing for the Charleroi scenario. So we'll go through these step by step. Just wanted to inform you that you can, on the datasets page on the website for the workshop, there's a spreadsheet that you can use to bring in your results for today's exercises. All right, so now I'm switching back to the input preparation toolkit, because we need one more thing before we can run an OpenQuake calculation, which is to set up the calculation, we need something called a job configuration file. OpenQuake jobs, they mostly refer to individual calculations. So again, we have some friendly interfaces for you to start building your own calculations. So we have tabs for earthquake scenarios, which is what we'll be using today. For tomorrow's exercises, we'll be using the event-based configuration tab, and then we have a couple more that probably we will not have time to touch upon. So what we're doing in this step is providing all the other configuration parameters for running an earthquake scenario example. So we are now under the configuration file tab, and under that we're under earthquake scenarios on the input preparation toolkit. So right now we're just looking at the hazard part of the scenario. So just leave the hazard box checked and the risk box unchecked. So the first piece of information it asks you for is to provide a short description of the calculation that you're running. So what this will help you to do is it lets you track the different calculations that you've run. So it has a history of the descriptions of the different jobs that you've run, so that you can quickly go back to different calculations and access the results from them. So here, let me say a Charleroi scenario. Median ground motion calculation. So I'm just providing something that will help me find this calculation again in the future. So then the next thing it immediately asks you for is to provide a rupture model file. Right now, let me clear. So that we start with a clean slate. So I have, if you click on the drop down button, you should see there's nothing there. Let's upload the rupture geometry file that we just created. So so under exercises, I've moved that file to the Charleroi folder. So I have my rupture file. So once it uploads, you should see that in your drop-down menu for the rupture model file. If it's not automatically selected, you may just have to click on the drop-down and actually select the file. So the next part is called the rupture mesh spacing. I just wanted to tell you that for each of these input parameters, there's a very short, brief hint about what is happening in that parameter. If not, there's a more extensive documentation in the manual as well. So here the rupture mesh spacing parameter is what OpenQuake will use to calculate the source to site distances. So if you have many sites and you're trying to compute the shortest distance to the rupture or The Excel file? It's the file that you just downloaded from the Ruptures tab. Once you download it, it goes into your downloads directory. Then I moved it into my scenarios folder. I renamed it to this Rupture scenario, and then you can upload it here. If you're working with a local version of the input toolkit, you're not really uploading anything. It's on your machine. It's just linking the files in the correct way. Yeah, so as I was mentioning, so the rupture mesh spacing is something that OpenQuake will use to discretize the rupture and then calculate the distance parameters from the source to site, source to different sites. So here, let's say, let's use a rupture mesh spacing of 2 kilometers. The only thing I would mention here is you can provide a very fine rupture mesh spacing, which will probably increase the accuracy of your distance calculations, but it would come at some computational cost. So there's always a trade-off between accuracy and computational efficiency. Questions? The rupture mesh spacing is only for the rupture. So you've modeled the rupture plane as a 3D geometry, right? It's the file that we provided. So now that rupture plane will be split into a mesh, and so then we'll create a mesh on the rupture, and then if you are computing the source to site distances, you'll use these mesh points for computing those distances. Yes, it's the distance between the lines of the mesh. As I was mentioning before, OpenQuake is very flexible, so that means you have many different ways of doing similar things, whichever is more convenient based on the information you have. So here the next section is on the hazard sites definitions. So this is, the question is, where do you want to compute the ground shaking at? Like, is it a list of points? Is it a region where you want to create a grid and compute the shaking at the grid points? Or do you have an exposure model and you want to compute the ground shaking at the exact locations of those assets, of those buildings? So there's different ways in which you can specify where you want to compute the ground shaking. For now, let's use the region grid. So we'll create a region, a polygon surrounding the rupture. Let's say going 2 degrees north and south and 2 degrees east and west. So we create a 4 degree by 4 degree polygon around the rupture and then compute the ground shaking within that polygon. And again, now the region grid is how finely do you want to discretize this region where you're computing the ground shaking. So let's say 2 kilometers for this example. And then again, you can experiment with higher or low values, and this will again be linked with the trade-off between computational accuracy and efficiency. So for now, let's say 2 kilometers for the grid spacing. And then again, now, if you, it's asking you, how do you want to define this polygon? Is it by providing the vertices of the polygon directly, or do you want to infer some kind of envelope polygon covering your exposure that you provided here? So if you have a group of assets, then you can ask OpenQuake to create an envelope polygon surrounding all of the buildings in that exposure model, and then you can discretize that into a grid. For now, let's just create a square region. So here, we've given you some hints about what that region would look like in the Excel spreadsheet. So you see the hypocenter is roughly at 70 west and 47.5, 47.6 degrees north. So let's try and create a grid which is, let's say, roughly 1.5 or 2 degrees north and south from the hypocenter, and 2 degrees east and west from the hypocenter. I'm going to input the same coordinates that you're seeing on this polygon here. If you're interested, you can also change those and see how that affects the ground motion fields and the run times. So remember that you're in all of these exercises, we're always inputting the longitude first and then the latitude, because we're looking at this as x and y coordinates. So we're looking at longitude and then latitude. So longitudes in the west are all negative. So here, let's say minus 72. So this is 72 west. So I'm starting from the top left and moving clockwise. So this is the top left corner, 49 north. The next point would be the top right. So this is minus 68, 49. The bottom left, which is minus 68, 46. And then since it has only 3 rows there by default, you can add in a new row and add in the last coordinate, which is minus 72 and 46. It doesn't have to be a square or a rectangle. If you have more vertices, you can input as many as you need to define the polygon surrounding your rupture. Everyone with me so far? The next section is on how do you want to define site conditions. Most GMPs, they use only one parameter to kind of take into account site conditions or amplification from rock to local site conditions, which is the shear wave velocity in the top 30 meters of the soil, which is called the VS30. Some other of the newer GMPs, they do ask for other parameters. For now, we don't need these two parameters called the C1, 1.0, Z2.5. We're just working with the VS30 in the Canadian GMPs. For the first example, let's stick with uniform site parameters. And let's use the default values of 760. And later on, you can upload a site conditions file, which is just a set of longitude, latitude, VS30 values in the area surrounding your rupture, if you have that information. Which we have provided to you a VS30 file clipped to this area of interest. So we can look at the difference bringing in site conditions next to the ground motion calculations. So that section for site conditions, we're just sticking with the default values, uniform site parameters, and the VS30 value of 760 meters per second. The final section is related to the ground motion prediction equations and some other connected parameters. So as mentioning before, all of the ground motion prediction equations used in the 2015 NBCC hazard model have been implemented into OpenQuake. They have, if you click into the GMP box, you'll see a drop-down list of all the different GMPs that are already built into OpenQuake. Usually they are called by the names of their authors, but not always. So the GMPs implemented as part of the 2015 hazard model for Canada, they all begin with the name NBCC. This is the National Building Code of Canada 2015. They're all AA13, so they're Atkinson and Adams 2013 is the publication that describes these GMPs. So all of them begin with the same letters: NBCC 2015, AA 13, and then if you look at the rest of the nomenclature, they describe the tectonic region for which the GMPs are applicable, and then so the first three are active shallow crust using the RJV distance, and then for each of these tectonic regions, you'll see three GMPs: central and a high and low variant of that GMP, as Michael was describing in his presentation in this morning. So in the Charlevoix region, in most of eastern and central Canada, we are in the stable continental crust region. So these are at the very end of the NBCC GMPs. So let's select all three: the central, high, and low versions or variants of this GMP. So if you click on those boxes, they should be selected for you. So in the scenario kind analysis, you can work with multiple GMPs, but there's no logic tree structure, so these GMPs are not assigned any weights. So OpenQuake will do the computations independently for each GMP that you select and provide you with the results for all of those GMPs, and then it's up to you how you want to, whether you want to combine results from different GMPs or look at them separately. But OpenQuake does not do that. In the probabilistic calculations, you can provide predefined logic trees with weights assigned to different GMPs, and then those would be used to compute weighted means and quantiles. So the first part is to select the GMPs. Then you can specify which intensity measure types you would like to compute the ground motion fields for. By default, there's PGA selected. But in the drop-down box, let's also select, say, spectral acceleration at 0.3 seconds and maybe also 1.0 seconds. If you don't see an intensity measure already appearing on this predefined set of intensity measure types in this dropdown, if you have a custom intensity measure type that you know that the GMP supports, then you can type that in here. Let's say, here I don't see the spectral acceleration at 0.2 seconds, for instance, but I do know that all of these GMPs do support that as well. So I can just type in here SA 0.2, and then ground motion fields will also be produced for that intensity measure type. For now, let's just stick with PGA, SA 0.3, and SA 1.0. The next item here under the calculation parameters is the ground motion correlation model. So this describes whether or not you want to model spatial correlation in your ground motion fields, because as I was mentioning before, each of these ground motion prediction equations provides you with not just the median estimate for the ground shaking given the magnitude and distance, but also a measure of the uncertainty through distribution. So if you are including or propagating the uncertainty in the ground shaking, then you want to be careful to model also the spatial correlation in the ground motion, because what you'd like to see is two sites that are close to each other and at similar distances from the rupture. You would expect them to see similar levels of ground shaking. So when you're modeling the ground shaking at different locations, you want to account for the spatial correlation in the ground shaking as well. For now, we are just producing the median ground motion field, so we're not sampling any values from the full distribution. So let's keep that at none. Another aspect about the correlation models is that the GMPs for the NBCC 25 model, they do not split the standard deviation into intra and inter event sigmas. So correlation models, spatial correlation models cannot be directly applied to these GMPs, but some of the other parametric GMPs do support this, and we can take a look at the effects of this if we have time. The level of truncation again is related to the sampling from the distribution of the ground motion prediction equations. Most of the GMPs, they provide you with, they assume that the distribution of ground shaking given magnitude and distance at a location can be described by a log normal distribution. So then the GMPs give you the median and dispersion or the standard deviation of this distribution. So the level of truncation is a parameter that OpenQuake uses to sample from this full distribution. So if it's essentially you're specifying here how far from the median do you want to go within this distribution to sample values of ground shaking. So if you say 0, that means you're always sampling exactly the median ground shaking predicted by the GMP. So since we're now interested in producing the median fields, let's set the level of truncation to 0. And then we're down to the last two parameters. The maximum source to site distance is a way for you to again reduce the size of your region of interest, because once you start going further away from the rupture, the ground shaking dies out sooner or later, and then so that you don't want to be calculating ground shaking 1,000 or 2,000 kilometers away from your rupture, especially when you're modeling smaller ruptures. So this is something that you can use to again tweak your computation time. In the stable continental regions, usually the ground shaking dies out after very large distances. Sometimes you can even see some damage 500 or more kilometers away from the epicenter. Here, let's keep this to 300 kilometers. And then since we're only producing the median ground motion fields, the last box, I'm keeping it as one ground motion field. So this is essentially telling OpenQuake how many ground motion fields you would like to simulate if it's a Monte Carlo type of analysis. Right now, we're just producing the median ground motion fields, so we keep this at 1. And that's it. We filled in all the required parameters to run a scenario, and we should be able to download a zip file that contains the rupture geometry and all of these calculation parameters in a way that OpenQuake can recognize. If needed, I can go through quickly again what the different parameters are, but for now, if nobody has questions, if everybody's following me, I click on download zip file. By default, the file is called scenario hazard.zip. Again, it goes into your downloads directory. And just to keep things organized, I'm going to move it from my downloads directory back into the scenario folder for the Charlevoix scenario. And I'm going to rename it to something that I can recognize, because I don't want to have multiple files with the same name. So this is, I would say, median ground motion fields. Charlevoix scenario. That's it. We've downloaded all of the input files that we need, compressed into a zip file. If you're curious, you can just unzip that file and see what's inside. It'll be the rupture file that you created, along with what's called a job file. It'll have an extension of INI, and it's just the parameters that we listed in the input preparation toolkit in a structured way. All right, if you've downloaded the file, we are ready to run the first calculation. So I'm going to switch back to the QGIS window. And if you click on the play button within the OpenQuake toolbox, you should see only one button here, which is run calculation. And I'm going to move to my, I'm actually going to do what Catalina suggested that you should do, which is to create a shortcut to my workshop directory, because otherwise I'll have to keep navigating to that. Workshops, exercises. So I'll create a link here. So I'm under exercises, scenarios, we're in the first scenario. And you just need to select the zip file that you downloaded. So it's, if you didn't rename it, it would be called scenario hazard.zip. I just renamed it to the Charlevoix scenario median ground motion fields. Click on open. So what the plugin will do is it will unzip that file, go through all of the input files that are within that zip file. And if there is an OpenQuake job, it will try to run that job. It will go through all the input files that are listed in the OpenQuake job. If you click on the console button, you can see a log of what the OpenQuake engine is doing. So this seems like it was very quick. It finished in 4 seconds. I have a pretty old laptop. This is almost 6 years old. So if you have newer laptops, it should be even faster than this. So it says there are 25,000 hazard sites within that 4 degree by 4 degree polygon, and we have 3 intensity measure types: it's PGA and SA 0.3, and 3 realizations, which means in this case 3 GMPs. So the calculation, when it finishes running, you should see, if you click on it, if you select the calculation, in the bottom window, you should see a list of all the different outputs that are generated as a result of this calculation. The main output that we are interested in is the ground motion field. So there's a way in which you can download all of these outputs as CSV files. So there's always a download button. If you have the output available in different formats, there will be multiple buttons, one for each format. But in this case, what we want to do is just visualize the ground motion fields within our QGIS project. So I'm going to look at the ground motion fields and say load layer. It opens up a window asking you what you're interested in visualizing. Since we have 3 different GMPs, we have a drop-down box where you can select which one you'd like to visualize. Let's say the central GMP for stable thrust. Then again, we have 3 different intensity measure types: PGA, spectral acceleration at 0.3 and 1.0 seconds. Let's look at the PGA map and just say OK. It loads the output as a layer into your QGIS project. So you should see something like what I'm seeing on my screen if everything went well. If you have issues, if you ran into errors in your calculation, we have Catalina and Nitik, and also we have the virtual participants. Michael as well is using OpenQuake before. So you can see on this map, we've also plotted the epicenter of the event, and also the rupture plane that we modeled. So those are also layers within the scenarios group. So if you go to the Charlevoix scenario, this is what is being plotted: the hypercenter and the rupture plane. So by default, when you bring in layers from OpenQuake results into this QGIS project, it just gets loaded as a layer at the top of your list of layers. So if you want to keep things organized, I would suggest moving them into the scenario that you're working with, and also probably rename that to something that is more informative, because you might have different layers with the same name. So let's say I'll rename this to Central GMP Median PGA. And all of these results get loaded as temporary layers. So they won't get saved to your disk unless you want to save them. Usually people just want to look at results quickly and discard them if needed, or keep them if needed. So if you click on the small, I guess it's a symbol for RAM. So if you click on that, it will give you an option to save that as a shapefile or as a geo package to your disk.
How you make your own option, the center GMP media, how you just create that.
Sure, yeah. So when you finish running the calculation, then you see this list of outputs, right, at the bottom. So in the ground motion fields, if you click on load layer, when you do the load layer, it gives you options about what are the different outputs you want to visualize. So because you have the 3 GMPs and the 3 intensity measures. Okay. You can save it like by clicking on this small icon here. Otherwise, it's a temporary layer that will get discarded when you reload the project. So if you want to save it to disk, you can click on this small icon next to the layer and save it either as a shapefile or a geo package to wherever you'd like on the disk. So that way it will be more permanent. Let me save it to the disk so that I have it as well. And let me call it. So if you loaded this as a layer, what you can do is you can do some quick checks on the data that is stored within this layer by saying right-click, and you can look at the attribute table. So this shows you the actual values for the 3 intensity measure types. So if you had seen the list of questions that we had for you for the 3 scenarios, one of the questions is, what is the maximum PGA that you're seeing in this in the region because of this scenario? So if you want to sort these 3 columns by descending order or ascending order, you can just click on the top of the attribute table column, and that will sort the values by first ascending, and if you click on it again, it will be sorted in descending order. So you'll see that the maximum PGA that we have for our example here is 0.8 Gs. So the maximum PGA might not be at the same location where you have the maximum, let's say 0.3. So if you order the ground motion fields by maximum spectral acceleration at 0.3, that might be at a different site, and you might have higher values than 1.09. We can check that by sorting. So you know that seem to be at the same site, 1.29 G, and you can do the same thing for spectral acceleration as well. We can also plot the maps for the spectral acceleration in the same way. Load layer. Let's take a look at the difference between the central GMP and the high variant of the same GMP for the PGA as well. So we can compare differences in the intensity. So we'll rename that as central. Now this is the. To make sure that I'm using the same ranges for the different colors. By default, OpenQuake will select some ranges for you based on the maximum and minimum values seen in that output. So you'll see that we have different ranges for the central GMP and the high GMP. So what I'm going to do is copy the styling from the high GMP by right-clicking on it under Styles, copy style, and let's copy all of the style categories. And I will use the same styling for the central GMP. So let's say paste style, paste all styles. So if I now look at the ranges, I have the same colors being used for the same ranges of ground shaking. So these are both PGAs, but one of them is the central GMP and one of them is high. So we can take a look at the difference between those fields. So this is the central GMP now styled using the styling from the high GMP. If I switch that off and look at the high, you can see the differences in the predicted shaking intensity just from the 2 different GMPs. All right, so let me just do one more thing before we move on to the next example, which is to load the spectral acceleration at 0.3 seconds. So spectral acceleration at 0.3 seconds is something that would be closely tied to damage or it's a displacement drift and then damage for low-rise structures, which would be very common in this region, low-rise masonry, low-rise concrete. So this is an intensity measure that is of interest for engineers. So this layer has also been loaded. Let me put that also into the Chalwa group and rename that to central GMP median spectral acceleration 0.3. And let's use the same styling for this layer as well. Yeah, so then here, this is what's called your canvas. So this is not something that you cannot put your color bars or the legends on this area, but there's a way in which you can produce maps for printing or more formal. You can prepare print layouts. So under the project menu in QGIS, if you click on New Print Layout, you can create different print layouts. Let's say so now your GMFs. And then you can bring in your map from the canvas here. So add a new map. So this is where you can add more information on top of your map. So if you want to add a scale bar or a legend, you can do those things here. So there's a button for adding a legend. By default, it will try to create a legend for everything that you have in your QGIS project. So you'll have to just switch off a lot of different layers. Sorry? Is one of these buttons here. So this adds a new map to the layer. It's from the QGIS project menu bar. There's new print layout. And once you create a layout, you'll see that in your layouts list. So you can create different layouts for the different scenarios. And if you want to keep something constant, you can create different layouts. So then this is all of the legends that we have. I'm going to switch off many of them. So you can add legends to your map as well. You can add scale bars if you are preparing these maps for printing or distribution. So you can add a scale bar with distance measures. Yeah, so that's how you do it. Again, if you compare the PGA with the spectral acceleration, you can see the different maps. So that's 0.3. So comparing between the PGA and spectral acceleration at 0.3 seconds. All right, let me know if everybody's here. Then we can move on to the next examples. Questions? So we've already done this, Claude. Okay.
Just doing it again.
Yeah. The next example will be very simple.
Yeah, if you repeat this one,
Okay.
maybe just like the exact same things that were repeated, they can get that. Yeah. Thank you.
So in the example that we just ran, you should have enough information to fill in this part of the table of the of your assignments. So just task 1, using the NBCC 2015 GMPs. The question is using uniform site condition, which is VS30 or 760 meters per second. What is the maximum PGA in this entire area? What is the maximum spectral acceleration at 0.3 seconds and 1.0 seconds for the 3 different GMPs? What I'm going to do before moving on is to do a quick recap of all of the steps that we just did. So the first thing that we did was to create the rupture geometry file using the input preparation toolkit. So we went to the earthquake rupture tab. We put in all of the rupture information provided by Tegan for this specific scenario. We inputted the magnitude, the rate angle, the location of the hypocenter, the rupture coordinates, rupture plane coordinates, and then we downloaded the file, the rupture geometry file, as an XML input file. By default, it goes into a downloads directory, so I moved it into my scenarios working area. So I put the rupture file into my scenario, the Charlevoix and Excitations scenario folder. Is this file, which I renamed so that I can find it better.
You make a new rupture?
No, I'm just going through doing a quick recap of what we did. Yeah. For those who missed some of the steps, I'm just going through the steps quickly. So that was the first step. We created the rupture file. And then we moved to the configuration file tab under earthquake scenarios. We're just looking at scenario hazard, which is producing ground motion fields. We added a short description of the scenario that we're running. Here we uploaded the rupture file that we created in the previous step. So it should show up as one of the options on your drop-down list. For rupture mesh spacing, we used 2 kilometers. Then we inputted a region grid with a spacing of 2 kilometers again. And we provided the coordinates of a rectangle surrounding the rupture, specifying to OpenQuake that this is the region where we want to produce the ground motion fields. For site conditions, we use a uniform VS30 value across the whole region, which would refer to rock conditions. For the GMPs, we selected the 3 GMPs for stable continental, for stable crust in the NBCC 2015 model. We are producing ground motion fields for peak ground acceleration and spectral acceleration in 0.3 and 1 second. We're not using ground motion correlation in this example. We're producing only the median ground changing, so we're using a level of truncation of 0. We increase the maximum source to side distance to 300, and then we're producing only 1 ground motion field. So after you input all of these into your tab, you can click on download the zip file. Again, rename it to something that you can recognize better before it starts cluttering up your downloads directory. And then we switch to the QGIS interface, clicked on the play button, and clicked on run calculation, where we provided the zip file containing the input files for the scenario. So this was the Charlevoix median ground motion fields zip file. If you click on open, it starts running the calculation, and you should see a kind of a log of what OpenQuake is doing in the calculation. It tells you how many has its sites you have, how many intensity measures you have, how many ground motion prediction equations you're using, things like that, and then it stores all the outputs to a database. And then the plugin has an interface to connect to this database of outputs and visualize all of your outputs, many of your outputs within the QGIS environment. So once you click on the calculation, you see in the window at the bottom half of the screen the list of outputs that are produced by that scenario calculation. You can download most of these as in different formats. Many of them in CSV, some as zip files. And for layers for outputs that you can already visualize in QGIS, there's an option that says load layer. In this case, the only one that has this option is the ground motion fields output. So if you click on load layer, it gives you different options about what you would like to visualize. So these are the different GMPs that you use, the different intensity measure types. And then if you're running a Monte Carlo simulation, then you'll have multiple events to visualize as well. Yeah.
That's what I mean.
Yeah, I think we're ready to
That we would have a break and then we can keep on.
actually, I'll make it.
Okay.
Can I just show something? Hey, I don't know if Aaron Todd is here. You were asking questions. Do you have a map layout window open?
The print layout?
Yeah. Sorry.
Thanks very much for sticking with us through this first exercise. For some of you, it probably went really smoothly. You found everything, went through it. For others, I know there were a few technical difficulties. Hopefully, you got help on those. If you're feeling kind of frustrated, like you didn't really get it, you didn't get what you wanted out of this one, don't worry. We found that by the second time you go through these scenarios, you kind of pick it up, and then it becomes a little bit more familiar. So anyway, we're going to take a short break, but before we do, I just wanted to take a moment to thank, again, our hosts for very generously providing our refreshments and our lunch as provided by Western ICLR Multi-Hazard Risk and Resilience Project, and we're very appreciative of their support to make this workshop possible. So thanks again, and we'll take a short break, and we'll be back for the last part of our exercise.
Okay. Aaron Todd, I don't know if you're here, rather than me trying to explain what this is. So once you open your map layout window, which is different from, like, this is the main QGIS window, and this is your map layout. So when you want to add a new map, so you click this little icon that adds a new map to the layout, and then you drag across your page, and it'll add a new map from whatever you're looking at in your main QGIS window. There we go. All right, I'm going to leave that because. Oh, actually, I'll also just say thank you to everyone from GEM and everyone else who's been running around trying to answer questions, and thank you to all the participants for asking questions and trying this out. That's pretty great. So I'll hand it back over to Andrew. Yeah, but I'll be online to answer questions. Hey.
For the online participants, we'll be back in minutes. Yeah. Let me just stop the recording for a bit.